So I'll say hello. I'm Micah. Welcome to the Bay Area D3 Meetup and welcome to LinkedIn. I will tell you about the night and then introduce our speakers. So we will have a talk and then some time to discuss and chat among yourselves some more. And then we'll come back for a panel discussion. And then after that, we'll have show and tell. This is one of my favorite parts. We show our D3 examples, things we're working on, data visualizations in the browser. So I'm really pleased to introduce our speakers. I'll go left to right and say we have Chris Olah, Ian Johnson, Ludwig Schubert, and Shan Carter. They are variously from Google and OpenAI, but for tonight, they're authors in distill.pub, a journal of machine learning, and then I also think like data understanding. And so I'd also like to say that I work at LinkedIn. We are hiring. If you would like to work at LinkedIn, talk to me or talk to some of the friendly recruiters out front. And then I think Chris has something similar to say about OpenAI.
Hello. So I lead the Clarity team at OpenAI. We're working on how humans can understand what goes on inside neural networks. And a lot of that's data visualization. We are hiring both full-time positions and fellows and interns. That includes the possibility of doing 6-month fellowships with us.
Fantastic, thanks. So now I think we'll go straight to Shan.
I'm Shan Carter. I also wanted to introduce somebody who's a couple of you who are not here. There's Zan Armstrong, who also worked on this article, and she works at Google, and Arvind Satyanarayan, who worked on some of the previous article, which is similar. Yeah, and then that's a good list of people right there, I guess. Yeah, Catherine Yee worked on some of this with us as an intern, and Alex Morbintsev, who's also at Google. In Zurich. So I always like to include everybody because I'm the one maybe presenting here primarily, but it's a group effort of everybody's work. It's mostly their work. Okay, so let's see. Oops. Yeah. Okay, cool. So okay, so hello, we're all introduced. So we're going to talk about, as Chris talked about, understanding how neural networks work. We're going to focus tonight mostly on just one type of neural network, a classification network. And basically, high level, it takes an image like that picture of any one of those, and it will have one of 1,000 predetermined text labels. So guacamole, toucan, Labrador. Actually, is toucan one of them? I forget, but there are 1,000 labels that it has to choose from. And there are millions of images. And so what happens is you feed it through this convolutional neural network, and then at the end it'll spit out what it thinks is the best text label. Or actually, it'll rank all the text labels with the percentage. But as you can see, within this neural network, there's lots of these layers. There's lots of complicated numbers going on. There's lots of vectors flowing through there. And basically, one of our deepest understandings, and we could go through and talk about the architecture of this and how it's all set up, but it doesn't really tell you very much about what's actually going on, especially if you don't have a degree in machine learning. And so ultimately, one of the fundamental questions that we grapple with is this one. It's any one of these layers is basically a high dimensional vector, like a 512 dimensional number. And so it's how does this neural network think about images boils down to how can we visualize a 512 dimensional activation space of any one of these several layers through this network. And there are many ways to do that. One of which is to use feature visualization, which is basically kind of asking the network to draw a picture of what it thinks is the most iconic representation of a specific place in the space. Okay? Does that sound reasonable? And so we can do that along kind of the basis dimensions of these 512 dimensions. It's kind of like when you're mixing colors, you have red, green, and blue. Those are your 3 basis dimensions. Any one of these has these kind of basis dimensions. And so here we've visualized 4 of them, and you can see one of them seems to be kind of concerned with buttons and maybe like electronics. One is kind of concerned with flowers. One is fabrics. And I don't know what that other one is, but chains. Yeah. Chris has done this. He knows, he knows this network quite well. You could say what number it is? Yeah. It's like giving out hex code numbers for web designers. Right? FF00, FF. So here, but this only gives us these kind of one-dimensional slices through this very high-dimensional space. So we can visualize any one of these neurons and see how much it activates, but it just gives you this thin slice through this space, which we visualize here with these pink lines. And we can, since these are just vectors, we can add them together. So we can add any two together and get a third one. And here you've seen we've added this furry one with one that's kind of like a pattern. I think it fires on like comics and money. So it's kind of like patterns and printed paper. And the other one just looks like dog fur or something. And you add those together and you get this kind of like furry money kind of dog fur texture. So any one of these dimensions you can seamlessly add together. This, if you just add two of them, you get these two-dimensional slices through this network, which is still a far cry from kind of what we want to see. And we want to see the whole space. And the other problem is that while those two I showed you did produce something meaningful, other random combinations produce things like this. So this is kind of a random dimension in this, a random direction in the space, and we've asked the network to tell us what activates that direction, and I have no idea what that is. And it's not really a realistic, reasonable, real-world image. So in essence, we're not actually talking about this 512-dimensional space. What we're talking about is kind of the submanifold of that 512-dimensional space that corresponds to natural images, like realistic. So we're kind of talking about realistic or likely combinations in this space, which is the submanifold. So one way we can do that is we can feed an image into the network and then see what activations come out of it, and then use those activations to generate these feature visualizations. So it's like we're feeding an image through the network, and then we're asking, hey, what do you think you see in that image? And then show us the like maximal version of the image that you think. And so the images, the networks work in little patches. So each little patch you feed through some pixels, which is that image patch. Then out of it comes this 512-dimensional activation vector, which is a point in the space. Then we run the feature visualization. So we say, okay, given that number, network, what do you think that number looks like? And then you can see what it comes back with. And you can do that for every point in the image. So here you can see on the right is the image we fed through the network, and on the, or depending on who is who here, left and right, I think you can tell which is which. The other one is what the network sees at each individual location of the image. And you can see there's like tops of dog heads, dog snouts, there's the cat stuff, there's just kind of like generic grass, and then on the top there's just kind of like blurry background, which is a little bit less specific than some of the others. And you can also see in the ears, it's like, there's kind of like floppy ears. And then there's like kind of generic dog legs, cow paws. But this feeding one image through the network and getting it out only kind of shows us these little pieces of this manifold. Because the network can classify thousands of classes. It can do it to millions of images. So what are the kind of component units that it's using to classify these images? Here we've seen how it can do one image. So what happens if we do this similar process, but look at 1 million images, chop up all those little pieces, and then put it back in together to get kind of a map of the entire space of what this network is thinking about natural images. And so that's what we call this like, activation atlas. So the process is we feed in a bunch of images. They each kind of give us activations, like we just saw in that one example. Then we put all of those millions of activations and use dimensionality reduction, like UMAP or t-SNE, to plot them into a two-dimensional space, because they're all 512 dimensions. And then we draw a grid around each one, and then do that same feature visualization on the clustered areas. And so here you can see a quite coarse one. And so you can see kind of the dog areas are in there, the grass areas, but you can see other things like people and floors and water and sky and fire. And basically this is like the alphabet of visual concepts that this network has learned about images. And here, so we can change the resolution of it, which is basically kind of a hierarchical. So here there's fewer of them, we can get more resolution. And you can go all the way down to like every single of the millions of actors. We can start to zoom in and see all the different parts of dogs that it's learned. There's like tongues, there's eyes, snouts, different parts of different mammals, different types of feet for different animals, different types of ground at different scales, water, they're like text detectors, gas pumps, keyboards. Some of those are like book jackets. It's like labels on things. Here's some fruit. Here's kind of this like human peninsula where there's like faces and hands, bodies and clothing. And so all of this is kind of like trying to expose what concepts the network is working with to classify images. So keep in mind, all we fed the network in was an image, and we told it to produce a label. That's all the network was made to do. It wasn't made to generate any of these images. It wasn't trained to do this. This is a data visualization of like the internal structure of the learned activation space. And so that's just one of the layers. So there's many layers throughout this whole network. And here you can see as you go deeper in the network, this one on my left is very early. The one on the right is very late in the network. And so you can see how concepts kind of get refined over time. The one on the left is very kind of vaguely foliage. It's like green. You get jackfruit, cabbage, corn, spaghetti squash, cucumber. It's all just kind of like green. Then about halfway through the network, we get a little more specific, and it's still a little convoluted, but those definitely look like leaves rather than green splotches. And then by the end, there's an area that's very specific to cabbage, and it looks like rounded leaves, and it's very specific to that class. This one, actually, these are old slides, so I kind of forget what this one is. It's like abacus, I think. So it's like, yeah, abacus. So on the final layer, they look like abacus, and then halfway through, that abacus also has keyboards nearby and spacebar, and then early on, like a cat. It looks like an eraser, traffic light. It's just things with these kind of like regular patterns. So you can see how the network through the different layers is kind of like really teasing out and becoming more specific about all the combinations. And each layer is composed of the concepts of the previous layer. So they're recombined into more specific and more complicated ideas. And here's one where kind of two seem to have been combined into one. The two on the left are from the same layer. They're from different areas. One is sandy and one is watery. And then by a later layer, you can see that sandbar contains both sand and sea together in a specific location. This is kind of interesting. So this is also an early layer, and you can see that like all the animals are just kind of like conjoined into this vaguely mammalian looking thing. There's seems like people-ish things, dog-ish things, but they're all kind of like just things with two eyes. As we go deeper in the network, humans and dogs have been separated out into two distinct regions. And then they get further realized as we go further in and further distinguished and specialized. Until the dogs now, you get specific breeds of dogs, whereas before all we had is kind of vaguely fuzzy things. So then how does we can also like kind of inspect how the network actually uses this like alphabet of images to make classifications. So this is a fireboat. I don't know if anyone, I didn't really know what fireboats look like before. Now I know exactly what they look like. So here's a fireboat. This is the area of the entire atlas that we were just looking at that activates strongly towards fireboats. And you can see it just activates in this one region. If we zoom in on that, you can kind of see how it might be classifying fireboats. Yeah. But you can see that a fireboat is composed of many different things. Like sometimes fireboats are spraying water, which is an attribute of fireboat. But then other things are just these red and white distinctive coloring. And here you can see fireboat at a later layer where it's all localized to one area, and fireboat at a much earlier layer where the concepts are much spread out and more commonly used between different classifications. So like the ocean area in fireboat is also the ocean area that's used for classifying sharks and stuff. So this is looking at an earlier layer for fireboat, and you can see it's kind of more elemental ideas that have not quite been combined into like one fireboat idea, but it's like, oh, there's windows, there's red crane-like things, and there's water and splashing water. And if we compare, oh, and here you can see how those three ideas might combine to classify a fireboat. And if we look at two similar classifications, a fireboat and a streetcar, we can see a lot of the activations are similar, but some of them are quite different. And this is a comparison of those two. So the first two is like windowed things, they're shared. Red crane-like things are shared. The water is very strong in one and not the other, and buildings are very strong in the other, but not the one. So you can see how this corresponds to a fireboat and a streetcar. So this is what the network learned as to the differences of those two classifications. And so we can kind of use a similar technique, but instead of just highlighting the areas, just remove all the other ones and redo it. So here's a closer look at that fireboat one, where you can just more clearly see what detectors the network is using to classify fireboat. You can look at scuba diver. This is red fox. There's a zebra, ladybug, knot. This one's interesting because it's knots don't necessarily come in like one color. Like rope is different colors, so you get this kind of like rainbow effect. When you ask the network, what is the best rope? It's like, well, it could be any one of these colors. And sometimes they all come in pill bottle, and so the other question is like, we were looking at two similar classes before, but can we do a little more systematized version of that? So this is a scuba diver and a snorkeler. So looking at the difference between the two. And here what we've done is kind of like an atlas, but on the y-axis, we've spread out the concepts, and on the x-axis, we've pushed one towards snorkel and one towards scuba. So the ones on one side are the concepts that contribute to snorkel and not scuba, and vice versa. And so you can see on one side, the snorkelers as expected, you get these like clear tubes and masks. On the right side, you maybe get like opaque masks and something that looks like a shark up there, which kind of makes sense. And it's interesting, so you can actually use that to kind of fool the network. You can take a picture of a snorkeler and add one of these component ideas and then switch its classification to that other class. And then here's frying pan and wok. And similarly, we can add noodles to it and kind of like trick the network into thinking that that frying pan is a wok because we've added this component idea that it has, is like causally confused as to like what noodles mean. But this one's interesting. So this is a gray whale and a great white shark. And then here there's something that looks a lot like a baseball, which is a little strange. And we can test it. We can add a baseball, and that works too. So looking at this, like something that looks like a baseball will switch the classification from a gray whale to a great white shark. And what we think is that the network is conserving detectors between the red stitching of a baseball and the pink internal of the shark's mouth and the white teeth, that there's this high frequency red-white detector that it's conserving between those two classes, and there was nothing in the training data that where it had to really distinguish between a baseball or a shark. Not a comparison that it had to make, so it kind of was like conserving this detector. And so here we've kind of like seen the shortcut it's taking and used it to kind of exploit the network, change the classification. Like no human would confuse that gray whale with a shark because there's a baseball floating in the water, but this network has that problem. So I think, do you guys want to talk about the comparison stuff, or I actually deleted it, but it didn't update. But we've used a similar technique, or Ian has. Do you want to talk about your stuff at all, or should we switch the article and take a break?
I think we should take the break.
Take the break?
Yeah. Or I mean, switch the article.
Yeah, so this is an article that's public right now.
If you keep tabbing, it'll come up eventually.
It'll keep coming.
I think that's it. Yeah.
Oh, that one's okay.
Those ones are.
So we have several articles along these lines. If you go to distill.pub, this one's activation atlases. Some of the other techniques that we've been talking about is like using this feature inversion technique to kind of explore the internals of the networks, and also other techniques. So this is kind of the most recent culmination. There are lots of other articles, which maybe Chris would want to talk about. But so here, this is basically kind of, I've given you a quick overview. If you want to learn more, this is a wholly interactive version of the atlases, and you can switch through all the layers if you'd like to see more in depth of all of these. And then there's a long description. lots of cool diagrams to explore. But basically, like broad levels, the reason that I'm really excited about it, like data visualization and machine learning, is that machine learning it has this black box problem, which I'm sure everybody's heard about, where these models, like this model particularly, was trained as a classification network where it had this very rigid API where it's like input an image and output a text label. And that's all it was like made to do. And as you can see inside this network, there's this whole universe of understanding inside of it. It's almost like, I always like to use this quote from about like, if you want to invent the universe, or if you want to bake an apple pie, you must first invent the universe, right? So it's like from Carl Sagan's Cosmos. But if you really want to classify an image correctly, you need to create a human level visual cortex basically inside. And it just seems a little bit of a waste to just use that to classify images one after the other. And so with data visualization, we can really kind of expose these like high level abstract spaces and that the networks have like learned and remapped, and kind of open up that understanding to humans and for us to understand. And so with these techniques is a way of doing that, is like taking the space and making it conceivable to us in a way that hopefully we can manipulate a more interesting way to classify images. And also like debug them and understand them. I'm more excited about like exposing the power of it in more interesting ways. So it sounds like we will take a short break. If anyone has any immediate questions, I guess all of us would be happy to answer them. And then afterwards, I think we'll have a little more Q&A, formal Q&A. Yeah. Yeah, so I mean, the kind of like concrete like safety problem is kind of the one that I was hinted at, and we have like more examples here. It's this idea that this is a problem, that this network thinks that baseball is a shark. Like that shouldn't be happening. And there's really no other way to really, I wasn't looking for that in looking at this network. I saw that happening and I was like, that doesn't seem right. Right? So there's no way to have tested for that if I didn't know that sort of thing was going on. So that's a very concrete.
I could build on that for a second.
Sure.
Interesting. Yeah. If I could, yeah. So I think there's also a lot of concern right now about bias in machine learning. So if we train these systems and we're having them make decisions that affect people, maybe they'll latch on to characteristics that we don't want them to make decisions based off of. And I think that, for instance, the frying pan and wok and noodle example, right, where part of how it's distinguishing between a frying pan and a wok is based on the co-occurrence of noodles. That's not causal; it's just correlated. And I think that actually sort of structurally is similar to a lot of the things you might be worried about with bias, where there's something that isn't causally connected to the thing you're concerned with, but there's something that's correlated with it, and the model will pick up on that. And we've actually had some other experiments where we've seen that the model even will just pick up on the gender of people that are co-occurring with objects and use that to slightly make decisions and things like this. So I think that's one place. And then I think sort of this is another thing that Shan was alluding to, that it's a problem that these systems aren't robust. I think you could imagine someday if we really succeeded at this and we really got to a point where you could go and look at how the network made decisions, that you could go and before you deployed a system in a place where safety was critical, you could really thoroughly audit it and go and maybe you could even get to a point where you could just give a mechanistic account of how the entire thing worked and sort of go and audit it like we can go and review code. So I think in the long run, that's sort of one of the things that I'm really excited about. Yeah, causal inference is a really hard problem. I think what we can do is we can see whether we as humans endorse various aspects of how the decision was made. And so if we understand how the decision was made, then we can start to go and explore that. And if instead we're just seeing the output decisions, we can't explore that dimension. Yeah, no. So in order to go and learn causal inference, you need some sort of prior about the causal structure, or you need an ability to go and evaluate the due distributions, the ability to go and run basically a trial where you intervene. So that's definitely not going to come out of this. But what you can do is you can have a human who understands the causal structure, who goes and looks at this and can evaluate whether it's doing the right thing. Sure. Well, or at least that a baseball isn't a shark. Yeah, could be.
So let's give Shan a hand, and we'll take a break now.
So now it's time to chat to your neighbor, to pull up the activation atlas and explore it yourself. We'll come back in about 2 minutes with time for more questions and a panel discussion.
Yeah, so if you want, it's just distill.pub is the URL, and it should be like one of the top.
Hello, welcome back. So I'm Micah. I will moderate a panel discussion with our esteemed speakers. I'll use this moderator's prerogative and ask a few questions, but then quickly turn it over to you all. I think we had good conversations in smaller groups, and I think there are a lot of interesting things to explore.
Before we get started, I just want to point something out that I noticed. Like we're happy to talk in depth about the machine learning side of things here, right? But this is still the D3JS meetup. We run Distill. We're super happy to talk to you guys about how we run Distill, how this article was built, right? Like everything's open source. We're super happy to answer any technical questions too. It doesn't have to only be about machine learning questions, although we're happy to answer these too. So whatever you're interested in.
Yeah, so I want to talk and ask about the technology stack, and specifically, like, what is the front-end stack, and how do you go from this metadata about machine learning to these beautiful images or these tools?
I think we use like everything. It's like, so on the machine learning side, it's like Python, it's TensorFlow,
It's big GPUs on Google Cloud instances. It's several of them running for days. On the front end, it's web components, kind of. It's Svelte, which is kind of like, I see, it's like Toledo. It's like there's one person from Toledo. It's like, yeah, it's kind of somewhat esoteric web framework that's similar to like Vue or React. Then there's D3, and then there's a couple other dependencies here and there. And then to the atlases, those are loading tile images that were created from those TensorFlow cloud compute things with some JSON, and then they're drawing it to a canvas here. It's actually two canvases, one on top of each other because of loading asynchronous problems, and I don't want to redraw too much. And then each one of these individual visualizations is loaded on demand as you scroll down the page, so that the whole thing doesn't pummel your mobile phone when you load it. Yes. So you can pull this up on your phone, and most of these visualizations still work with touch events, and all that stuff is a real just pain in the ass.
Well, don't forget. Yeah.
More pain.
No. I was going to say it's actually less painful because Lucid, right? On the machine learning Python side, these guys made a whole framework for making these kind of visualizations. And
Yeah. Can you show us Lucid? Tell us more.
yeah, so it's not like you have to go and learn everything from scratch and invent the universe, like Shan was
So on the
saying.
machine learning side, maybe Chris, I'll click on it.
Yeah. Well, actually, maybe go to the Lucid homepage instead, or to the GitHub page for Lucid.
Well, I just wanted to mention something.
Oh, yeah,
right here.
please, yeah.
With each one, there's a collab IPython notebook. Very visual. Click on that. You're in Python, IPython. That's connected automatically to cloud, free Google Cloud GPU. So you can actually.
I think in fact it doesn't say, like there's a JavaScript variable that didn't save, so that or something. So that, yeah. Well, I think the notebook works. I just think that it doesn't by default. Should the.
Is that the one?
Yeah, that. So maybe I'll. Well, maybe just scroll down to the list of notebooks for a second. So not only do we have those notebooks for that paper, but we've been doing this with all of our papers. So for every experiment in all of our papers, there's a notebook that you can just go and click on and reproduce that experiment in your browser. That's one thing that I think we're kind of proud of. Yeah, I think that Lucid makes a lot of these techniques pretty easy to use, especially if you want to visualize a model that's already in our model zoo. So importing your model is still a little bit, your own model is still a little bit annoying, but if you want to just go and visualize, say, Inception V1, you can literally, like, for instance, open the tutorial notebook, and you can start hitting Shift-Enter. And give it a second to, allocate the GPU and go and import the libraries and so on. But I guess that certainly within 120 seconds, that will have run. Yeah, so if you're interested in visualizing neural nets and doing feature visualization, apparently we're getting some warnings because TensorFlow's API has changed. But bear with us. It's not that hard.
Not enough technology.
I mean, maybe one other thing is that the fundamental technique underlying this feature visualization, there's an entire review paper that we wrote on this. So if you're like really interested in understanding how that algorithm works and that visualization technique works, there's this more basic paper on visualizing individual neurons. And you can see, well, yeah, you can just read through this. And again, every experiment has a notebook that reproduces it.
Talk more, and maybe this one is gone. Can you talk more about the difference between visualization for communication and visualization for tools for research? I think I see some of both, here, but I imagine there's some difference, and maybe some difference in time when they're developed.
Yeah, so I think Distill, which Shan and I founded, and Ludwig and Ian and many other people have contributed to, is this new scientific journal. So normally a scientific journal is, a physical thing, or at least PDFs, and doesn't really allow you to have interactive diagrams, and it's kind of written in this very formal way. And so we wanted to create a place where people could experiment with explaining things better, and using interactive visualizations, and sort of exploring that. And so a lot of the visualizations that we make for these are sort of more, some of them are more pedagogical in nature. So for example, like here's a little visualization that's doing a literature review and just summarizing how a bunch of papers shaped the space and introduced different techniques and are related to each other. And so that's not a visualization of a neural net. It's just a sort of explanation of how the literature there evolved and helping somebody understand that. But there's sort of this other thing that's going on, which is that we're also really interested in, one of the main questions that we as researchers are interested in is how can humans understand these neural nets? And so then there's, sort of this whole other way that data visualization comes in, where we're sort of trying to build, like the actual research problem is how do you build an interface that a human can use to understand these systems? And I think there we've sort of discovered that this is a really sort of rich problem where it's the systems that we're visualizing are very different, I think, from doing normal data visualization, and there's a lot of really exciting problems. And just like you have line plots and so on as sort of fundamental primitives for doing normal data visualization or graph layouts or things like that, we have all these techniques like dimensionality reduction algorithms, which take high dimensional spaces and try to preserve different aspects of low dimensional spaces, or feature visualization, this technique that we've been telling you about, or attribution, or various things like this. And those are sort of our fundamental building blocks for creating visualizations in the space, and that's sort of what we're exploring. Yeah, I mean, actually, we were really lucky to have Arvind Satyanarayan with us, and Arvind's now a professor at MIT, but he was with us for a year, and he's sort of very interested in sort of systematically thinking about visualizations, and helped us frame this kind of space of visualizing neural nets as just like there's a grammar of graphics that you can use to think about, about normal data visualizations, trying to think about what's the space of visualizations that you can create with. Sorry, was that a sign that I should be quieter? Oh, it's a sign to make the text bigger. I was like, do I have my mouth too close to the mic or something? And you're like, go and make it further away. No. Yeah, so that's I think that was a really cool thing. One question that I'd actually like to ask the group is, why do we think this is important? Because I think that actually there's a whole bunch of different motivations behind this, actually, I'm particularly interested in Ian's take on this, because I think he wrote an essay sort of exploring a really interesting motivation, and then maybe we can talk about some others.
Sure. I guess, why do I think it's important?
Yeah, or why is it interesting to visualize neural nets, or and maybe also how is that interesting for the database community?
Yeah. So I guess for a little bit of context too, before I had coffee with Shan one day, I really didn't know anything about neural networks, and I've doing a lot of D3 for a lot of years, and these guys kind of taught me a whole bunch along the way. And so one of the things that I kind of like doing is looking at these techniques and saying, well, how can I use that to do stuff I used to do, the kind of the D3 way? I guess what Chris is pulling up here is actually more, the first thing was, how can I do the D3 thing to machine learning? So they gave me a model and everything, all the numbers I could get access to. I was like, how do I put those on the screen? And so that's kind of always my starting point, is like, I have some data, let me see, can I draw some rectangles or circles or a bunch of them? And and see if we see any patterns. But then especially with this latent, the activation atlas thing, right? Shan showed how we can surface the concepts that the neural network has learned. But we can then take that and say, okay, if we can organize stuff by the concepts, right? So I don't think he explicitly called it out, but you notice how that map is kind of smooth, right? He said, okay, there's all the human stuff over here, all the dog stuff over there. And the similar things were close to each other, right? So you have all these fruits in this area, and then it sort of slowly transitions to some other concepts. What's happening there is that we can actually, here we're focused on the concepts, but that's actually the underlying data is being organized. So we think about it, the neural network is helping us kind of, you think about your data set as a giant, million-piece puzzle, and you open the box, and there's no cover on the front either, right? Like you can't see you can't put the puzzle together. And just from looking at the pictures, you don't even know what the edge pieces are. You just throw this box on the table, and you start looking for similar pieces, clustering them, right? What this is doing is kind of organizing it all together so that the things that are look kind of like to each other will be in a pile close to each other, and then you can start putting them together yourself. So I'm excited about being able to do that with all kinds of data sets and if you have a model that can learn. So this is an article I wrote about looking at the quick draw data set, right, which is millions of people drawing millions of drawings as in 20 seconds, prompted in this game that Google released. And then a researcher at Google trained a network to learn how to draw from those. And kind of like Shan was saying, like that model was only intended to just to spit out a drawing for you that was kind of realistic. And you could start the drawing, it would finish it for you. But using these same sort of family of techniques, we're able to just organize all the drawings so that similar drawings would be close to each other, and you can kind of find patterns and interesting groups. And in this article, I go through kind of, because this data set was open source, many people applied a more traditional data viz techniques to it. But you get to kind of see the qualitative difference of the kinds of patterns the groupings you can find in there.
Quickly summarize the question.
Yeah, okay. So what was the interface between machine learning research and interaction designer or visualization person? I'd say our boundary was pretty, in some ways, Chris is one of the best machine learning researchers I know about, but also, right, yeah. Well, since I've learned some things and I've Googled around, still the best. But he can also, write some mean D3 code. So it's not like, he didn't know anything about what I like to do. He's also very patient, and Ludwig and Shan too, in explaining concepts that, I could ask the dumbest questions and no one would say that's a dumb question, and patiently explain it. So there was a lot of transfer and it was a very safe space to explore. So I could get some data from them, the output of some model, or they would show me like, hey, you can access that internal array or whatever you want this way, or here's a Python notebook, here's how you use a Python notebook, and here, let's save a JSON file. And then once I have a JSON file, I'm off to the races, and I'll make a little visualization, and they'll be like, okay, that's cool, but doesn't really show us anything. Or be like, oh yeah, let's try it. What if you added this? And there's a very conversational experience, and I think that I would also advocate for that if you have some kind of influence over the way people work.
That arise out of discussion between the two of you, or was that handed to you?
So I want to talk just a little more broadly because this is something I feel very strongly about. But I don't know, how many people here like self-identify as a designer? Anybody? How many people here self-identify as like an engineer? How many people here is like, I'm both, I'm kind of like in between? Yeah. So like, to me, this type of work basically, there's a traditional like boundary between engineering and design where it's like, okay, I'm a designer, I made this red line, I mocked it up, and now I'm going to hand it to a designer or an engineer, and they're going to build it for me. Or an engineer comes to a designer and is like, hey, I made this thing, this is what it does, can you make it look pretty? And I feel like those kind of like boundary decisions between those roles is really unhealthy for building like really holistic, great products. I think similarly to research, this idea that like, oh, I'm the machine learning researcher, I'm going to train the model, and then I'm going to hand that model to somebody and they're going to make it interpretable is sort of that similar problem. And so I think all of us kind of like subscribe to this really like interdisciplinary where we all like that boundary is really fuzzy between those. And to your specific question, I don't think any one of us can point to anyone who's like, hey, I came up with this idea and then I handed it to you to implement the JavaScript part of it. You know, it was like much more of a conversation, like Ian said. Like I think
Activation path arose out of conversation.
yeah, because I think what Ian was showing earlier, where it's like, oh, here's a model that somebody gave me, and it has a bunch of numbers. I'm gonna like encode those numbers in visual variables on a screen. It's like that. We kind of learn quickly that only gets you so far, and that you need these kind of more intermediary, where I'm actually kind of like, I always think about it as like getting my hands in, like taking the hood of the car open and like pulling out all the wires and getting in there. I can't just like repaint the outside of your car and make it work better.
Yeah, I think we're in a very lucky situation in this particular arrangement of people, in that processes like these to me start a lot with respect for other people's work. And so I don't want to say like this doesn't transfer to your workspace, but I want to say that I feel very happy or very, very lucky to be in this particular team. And I mean, Ian joked about it, right? But I really think it comes down to people like Chris being very patient in explaining these concepts to us until we really get them, and Sean being very patient with me building front-end code that doesn't always work the way that he wants to, right? And I'm not sure it's really possible any other way if you want to collaborate with people other than to have a good understanding of what they do and what they're good at.
I wanted to add, this really goes all directions. So I've like learned so much from working with Sean, and admired his work beforehand. Prior to working at Google, Sean was at the New York Times on the graphics team when they were, and they still do amazing work, but I think that was really a period where they did incredible work. And Ian's done all this incredible data visualization work. Sean taught me how to use Adobe Illustrator. Now I go and I mock up every, all of my diagrams that I'm just copying and pasting and using his screenshot copy paste thing all over the place. Yeah. And I think also, the conceptual progress, I think, is also really, involves everyone. And so, I remember one time sitting at a whiteboard with Ian, and we'd sort of, we had feature visualization. We had this technique for going and sort of studying what neurons were doing. And we were thinking about, there sort of was this interesting thing where you could take the activations, how much each neuron fired. And you also now had sort of a visualization of what each neuron did. So you could be like, oh, the floppy ear detector fired this much. And Ian sort of had this framing of it being a semantic dictionary, where previously you just had this list of numbers that wasn't very meaningful to humans. And now we had this new object and this new interface and this sort of new way of thinking about it. That's this right here, right? So you have can you zoom in so that we can see the list in the dictionary? And so I think one of the things that you're doing that matters is sort of trying to figure out how to think about these systems. there's sort of this really interesting back and forth between, I think, thinking about interfaces, thinking about math, often like bringing in, interesting mathematical tools like matrix factorization and then backing that back out into interfaces. And I think it really ends up being.
Well, yeah, I just wanted to riff on that because I think this idea of sharing capabilities or gaining capabilities is something that always stuck out to me. Like, Chris understands what matrix factorization is, and I don't, but he could tell me why it's important and what I could do with it. And then I could then think about what I want to do with it. And then I could say, hey, can we do this? And he'd say, oh yeah, just, here, let's run this on that. And so that's also what I mean by the conversation thing, was that you can focus on that sharing of capabilities part too, right? And you mentioned like Shan being able to teach you Adobe Illustrator, but a lot of that was the capability of communicating your ideas a little better and getting us all to sort of speak the same language, or meet somewhere in the middle. I think that you can see it over the progress of these articles too, right? Like from feature visualization to building blocks to activation atlases. I think that's also why Sean's saying it's hard to point to any one thing, is that we spent so much time getting each other shared understanding, that someone might be like, oh, with that capability, maybe I can do this, right? But you're not going to trace it back that capability came from 3 previous things that somebody, that you all worked out. Yeah.
And we also invest a lot in making our tools easy to use for ourselves. Like that may sound like weird, but like the linear combinations of neurons, I sort of just tried that out because we built the API in Lucid in such a way that you can literally just add optimization objectives, as in like with the plus operator. And if you make it that easy, then it's a lot easier to explore these spaces, right? There's maybe like a technical adjunct, but definitely important.
So, a question. You have tools, but we still have a vast space to explore, or at least from an outside perspective, it feels this way. In the article, you focus on certain points in the space or certain layers. Can you tell me about how you find that focus, or how you approach like a really vast space?
Well, I want to say something before we dive into answering.
It may be worth clarifying whether you talk about the design space of visualizations or the literal activation atlas network activation space, the second one. Okay.
Well, I wanted to say something on the first one, which is I feel like one of the things that's really exciting about this space is it feels to me like we're just in the middle of this field that, like, there's all these directions that literally no one's explored before. And I think all of these like fundamental new visualization techniques to be invented. And I don't know, this is maybe a little bit arrogant, but it feels to me that we're like, somewhere around, like what's his face going and inventing the first, maybe like inventing the first line chart, Playfair inventing the first, Sean knows what I'm talking about, the first line chart and showing, imports and exports from Britain instead of a table for the first time, or things like this. And I don't know, maybe that's like a little bit of a grand way to describe it, but it just feels like there's this entire like domain of techniques for us to build up, and it's we're just like starting to scratch the surface. And I think that if other people want to work in this space, there's a ton to be done.
Well, the thing, I guess, I'll ignore your question. Keep talking. The thing that I get excited about is it kind of comes back to this question about like, what are computers for? Always for me, it's like, why are we even doing any of this? And to some degree, I think a lot of this is kind of like bringing this power to more people. And right now it feels like locked away among, it's like, just because I know math, I can dictate what we do with this technology. And I don't feel like that's the right answer for this. So both making these things understandable, and like we were saying, like Chris is being like really approachable to non-machine learning people and spreading that knowledge, I think is also part of that vision. But it's kind of that more humane vision of this thing, and trying to like make it accessible to as many people as possible, both through our articles and through the techniques we're describing to other engineers to make it more approachable. I think that kind of like really infects all of our work and kind of like is a little bit of a foundational layer to what we've been talking about.
Well, I'm going to now riff on something Shan said. And so people talk a lot about making machine learning accessible. And I think a thing that a lot of the time they mean is something like, oh, let's make it easy for people to go and train new machine learning models or something like this. And to me, that's not the interesting version of making machine learning accessible. Like even as a machine learning researcher, I don't train, I use Google and I use Google Translate and I use Google Photos instead of going and training my own machine learning model. And instead, it feels to me, and Shan might be able to speak more to this because I think he's thought about it a lot, but it feels to me that like instead there's this really exciting alternative vision of what machine learning could be like, where it isn't these like models that just do a single thing, but instead it's kind of this like rich thing that you can interact with and play around with. And it's sort of like, I don't know, it's also like computers right now, like just general computers, like, being able to program is it's this kind of amazing thing where you can get computers to go and do all these different things. You can create all these different visualizations. But a lot of computing has been moving in this direction of being instead, like a word processor that does a thing for you, or, a web browser that does a specific thing for you. And it feels to me like machine learning is actually starting at like the far end of that spectrum where you have these systems that just do the single thing. And instead, I think that there's a vision potentially of machine learning that isn't like that, where instead, you have this like rich space of representations, and these representations are objects that people can manipulate and work with and play with. And I think that would be a very different world. I'm going to now just ask Shan to talk more about that.
That was a beautiful description.
Yeah, I think that's I mean, we can just talk all the way. If you, what was Micah's question? Sorry.
So how do you approach?
Oh, the huge design space. Do you want to talk?
Well,
No, it was not the
Oh.
space.
no, not the design space, but the actual like space created by the model, right?
Oh, like how do you explore
Like
that?
yeah.
It seems that some parts of it are more interesting than others. What is your function for interaction?
Yeah, a lot of times I sit in front of these things a lot. I'm like, this is really hard. This is really complicated. There's a lot going on here. Yeah, it does. To me, on the inside, this all feels like a continuum, and sometimes it's hard for us to know like where to draw the line and like when to release an article or when to like communicate the results. Like with the Atlas, a lot of people were asking great questions that I was also asking, or I mean, but like, oh, can we compare two of them? Can you like, what does it show about this scenario? And I'm like, yeah, I wanted to do all that, and I wanted to keep exploring that. But it's like, when do you draw the line? When do you start exploring? What do you include and not include? My training as a journalist, I feel like I'm pretty good at editing, so like that comes fairly natural to me. So it hasn't been that hard to like learn what to include and not include in the article. But sometimes I get like excited by these rabbit holes and kind of get lost in exploring all these like weird spaces and kind of forget where I'm at. I don't know if any of that is.
I still think that was not the question, but obviously I need to follow up on that. One example of that for me was where those adversarial examples, those baseball plus whale equals shark things, that was not something you set out to do. Like it was literally looking at these charts that at one dimension, Tisney, the other one, the attribution to two classes, and just seeing something that looked out of place, right? I feel like that is literally what like explorative data analysis is meant to be, and that's where it turned out to be. And then of course you have that rabbit hole, and you need to do a qualitative evaluation because it's a scientific paper. And yeah.
I have a question to ask you. So having done the visualization, now allow you to go back and determine how to train networks more efficiently, more effectively. Artifacts like baseball/shark mouth correlation.
There's at least two ways to answer that question. A super short one might be not yet in a way that I can point you towards. A longer one would be we're working on two versions of that. You can definitely retrain models to try to behave differently, and you can think about like setting up new models, right? You could try to use these visualizations to compare the two models and see whether it achieved what you wanted it to achieve. both of these things are open research problems for us, and I'm not aware of anybody in that space having particularly insightful ideas. That's a very negative view of it. Maybe Chris has like a better way of saying it, but we're definitely working on it.
Was an OKR for our team last quarter. We have a red box under it. Hopefully we'll do better next quarter.
Well, I guess one thing to point out that's interesting though is that now we can see those problems, right? Or like Shan sat there and he saw it, and I think that's a huge change on its own, right? And it kind of, to Micah's original question that no one wants to answer, is that once you can start looking at things, then you can figure out what's interesting. So, and I feel like, I mentioned the feature viz article, the building blocks activation. When Chris first started talking about feature visualization and with Ludwig and Shan, and I remember like many of those ideas were brought up, right? Like, we didn't have an idea about the atlas, or, there's 6, 7, 8 types of visualizations and building blocks we explored, but some of those ideas were in there. But like once you could see a neuron as an icon, like we call it an icon, semantic dictionary, right? But it becomes something that like a person can reason about, that you can point to, right? But when you think about an array index, that's not really a thing. It's very ephemeral. I don't know, memory gets wiped, whatever, right? But you could print one of these icons, and we did, and cut them out and make pogs or whatever. And yeah, 1,000. And it's a thing, right? And someone can say, hey, like when this thing does that, right? What happens? Or you can start asking questions, you can reason about it. You say, what if we add them together? What if we spread them out and put similar ones close to each other? What if we measure how much each one contributes to the next one, right? Like,
or could you build a Firebase?
Right.
Here's the piece to try to build.
Yeah. So I guess the being able to see something and like talk about it, hold it, I think is a huge part of all this, and I think really relevant to us as data visualization practitioners. And then kind of also what Chris was talking about in terms of how rich the space is, how much there's to explore, and how kind of overwhelming it feels. Like, I think there's also something really exciting about building these interfaces. I think that to me was a really exciting part about the building blocks article, was how many ideas we tried, how each one, like the trade-offs, and like what we could express with one, but then what was missing, and causing us to pursue different things to address different, right? I feel like there's still so much more of that to do, and there's so much interface, but now instead of just having like filtering and numbers and stuff, you have all these high level concepts that you can start calling as functions or talking about or grouping, right? I don't know, it's a very exciting.
One other thing I wanted to say in response to Micah's question is, I think when you look at these atlases, right, the thing that is sort of most immediately viscerally exciting tends to be, where's an atlas? Here's an atlas. It tends to be these later layers where you've got things like, I don't know, let's zoom out a little bit. Like here we've got some crossword puzzles. It's pretty cool that the network, like, has crossword puzzles as a concept, and like that's what it sort of looks like to it, what a crossword puzzle looks like to it, and slide rulers and digital clocks and keyboards, and gosh, it's really cool that it has all those concepts. Or it's got this entire manifold of dogs over here. Lots of dogs. But I think actually one thing that has become really fascinating to me as I stare at these models more and engage with them more is also what's going on in other parts of the model. Where did my Google? I had this open, I thought. What? I deliberately opened. Yeah, that's okay. Okay, well, I think that you see if you look at these earlier, here, how about I just look at, so appendix. Let's look at 4A, for instance, right? And let's go down here. So this is a fairly early layer. And one thing you see is there's all these shape detectors. Like there's a cross detector here of like lines diverging from a center, or like this is, I don't have exactly a word for it, but some kind of like 3D geometry thing, and another one, curvature one way, spheres, circles sort of in another direction. There's lots of circles in various orientations are a very recurring theme. Curvature away from the middle. Just like, again, different kinds of geometries. Like here's some kind of like vase lid type thing or something like this. Triangles, squares. I don't even know what to describe this, but like sort of like lines converging and then a circle. Another, like just a circle like this now. Another circle, another square thing. And you just see all of these things, and they're a much lower level visual primitive. And I think, when I initially looked at these, I was kind of like, meh, I want to see dogs. I want to see animals. I want to see these like high level things. But as I've sort of engaged with these models more, I've actually become excited, and maybe I'm like most excited about these lower level parts that initially weren't exciting. And so I think that actually, like, the more I engage with these, the more I'm just like excited about the entire space of things that's going on inside the model.
Talking about the space, could we perhaps look at the atlas and I ask you a question about the coordinate space?
Yeah, that seems like a thing maybe we can.
And so while we look at it, I guess the way I'll frame this question is, we have an XY coordinate space. What is that? And then I see small plots for the layers. Do they share a coordinate space, or are they different but analogous? How does that coordinate space work?
I'm sorry, I wasn't listening.
It's not precisely the same space at the moment. Each of those are the result of a dimensionality reduction algorithm, right? The details don't really matter too much. We used UMAP. It worked marginally better than Tisney. You can use whatever you like. So in a sense, it preserves similarity a little bit, like on the conceptual level. We do, in fact, have ideas for aligning these atlases between layers. But it's a harder dimensionality reduction problem. So if any one of you is interested in writing dimensionality reduction algorithms with a lot of customizability, we'd be super interested. But yeah, the XY coordinates are an arbitrary result of the dimensionality reduction.
Sort of just talking about that a little bit more broadly. A lot of the time in machine learning, but probably also in problems that you work with, we're working with these really high dimensional spaces. So instead of having 2 dimensions, we might have 1,000 dimensions. I mean, in this case, it was only hundreds, but there's other cases where I've worked with things that have, tens of thousands of dimensions. And how can you go and sort of reason about a space like that? Well, you aren't going to be able to preserve everything. Obviously, there's going to be a lot of stuff going on in a 10,000 dimensional space that you just can't project into 2 dimensions. And so dimensionality reduction algorithms usually they sort of have this flavor of pick your poison, or actually pick the one thing you don't want to sacrifice, and then you pick that thing and you try to go and you optimize the positioning of your points so that you maximally preserve that thing. So PCA is one dimensionality reduction algorithm. And it sort of tries to preserve the global geometry of the space, but the global geometry of the space is such a difficult thing to preserve that you only get to preserve a tiny little bit of it. And T-SNE and UMAP, on the other hand, are these algorithms that say, okay, I'm going to give up on all of the global structure of the space. I don't care about that at all. The only thing I want to preserve is the local structure, what's really close together, the topology of the data. And I'm not going to care about anything else. And so this algorithm, it doesn't care about the relative positions of things on a large scale. All it cares about is keeping the points that are really similar close together.
Nope.
Maybe 1 or 2 more questions from the audience.
No.
There is a JavaScript both of TC
Yes.
and UMAP.
Yeah, so it's not in D3, but it is available in JavaScript. There are, I think, for both T-SNE and UMAP, some observable HQ notebooks that are pretty good explanations of those libraries.
Depending on your data, it for these particular things, it may make sense to pre-compute them because they're quadratic in the number of data points, because they care about distance, and they are iterative optimization processes that can take thousands of steps. So it's an expensive thing to run.
But I've also noticed that, because I've done the JavaScript and I've done the Python version, and still on my MacBook, I can do way more data with a Python implementation way quicker. And it's not that hard to just say, like, I'm going to save this CSV that's, maybe 80 megabytes or something, right? Run it through Python, save out the XY coordinates, and then do something with that in D3.
Another question. So perhaps a reinforcement learning question.
It's really hard. I think there's just so many directions we'd love to explore that we have to pick between. Yeah, I don't know. We have meetings. We go and gush about how exciting a bunch of directions would be, and then we see if there's somebody who is excited about a direction that instead of going and working on the other directions, they want to work on that one, and then those are the ones that we work on for a little bit. I think that's basically the algorithm we're following.
We also go to meetups, right?
Yeah.
To do it for us, or to come work with us.
Yeah. I mean, this week I'm working with Shan actually on trying to make a Python library and I guess JavaScript thing to make these atlases easier to generate, and maybe a sort of simpler version without needing the feature viz. So being able to take any data set where you have run it through UMAP or tsne and then let you custom render the grid cells, but make it easy to generate those tiles. And it's kind of like making a cartographic map, but of a high dimensional space. Because I believe that if we can make that easier to do, then many more people can explore many more models and data sets. And then once they do that, there'll be more ideas, I guess. Yeah.
Maybe one more question. I saw one in the back. So a question about convincing researchers to use these visual tools in their own work.
It's a very fair question. I'm not sure any of these tools are fully ready to easily be used in training neural nets. Parts of the insights that we've had looking at these models, we've been able to communicate clearly. One of the earliest articles that Chris and Sean, I think Augustus Odena wrote, was on checkerboard artifacts in gradients of certain models with unevenly aligned striding patterns, right? And that's just a mathematical fact that you can state in a paper, and the research community, then they can decide whether to keep doing this or to not do this. It's a lot more complicated with these sort of qualitative tools, right? Because even when you look at this and you understand the concepts that the model sees, it's not immediately clear at the moment what you would change about the entire setup to have an influence. And in a sense, that's what we're working on, right? That's one of the things that we're working towards, definitely. I will say, though, that many people are quite excited about seeing visualizations of their models, right? Because they've been working on these things for a while and they don't really know what they do, and it's kind of interesting to see.
I think there's an element of, I really wish that we haven't got that much buy-in so far. So we do have some success stories. I'm really hopeful that the machine learning community will I think they're sort of right now is this is cool, but not really people applying these techniques. And I really hope that in the future we'll see more people applying these techniques. The people who create the models that we visualize as sort of our standard models tend to be very excited about it. I think actually, a lot of the problem is actually just kind of relatively boring software engineering barriers, where deploying these models, so the algorithms that you have to run to go and do these visualizations are non-trivial to implement. And it turns out that there isn't like a super standardized way to go and like sort of trade machine learning models back and forth. And even when people go and store their like save out their models, they often don't save all the information you need to run it. So they don't like actually one problem that's kind of like an embarrassingly simple problem is nobody goes and anywhere has a like at least for TensorFlow that they don't go and standardize what the input range is. So should pixels be between 0 and 1 or 0 and 255, or another popular one is negative 117 and 255 minus 117, and there's all these things, right? And you don't know, so even if somebody gets you a model, you don't know which one of these it is. And so just like these like sort of annoying barriers just make it really painful for people to go and just like save their model and give it to us to visualize or go and run it in our system. And it's just enough of a barrier and that people don't use it very much. So that's hopefully something that we can work on.
If you're a software engineer, perhaps an area to contribute. Another question in the back, then I'll ask the speakers for some closing thoughts. Yeah, so the question is, how would you apply these tools to non-image domains or data sets from other domains?
We've had some successes. Well, one of our colleagues has had some success applying these to audio models. But it's still a fairly similar kind of model in that it's like still a continuous input domain, still 2D. And so that doesn't validate it really that far, right? So I think there's significant challenges in applying this to a discrete problem. So as soon as your input's discrete, you can't just get gradients and go and optimize anymore. You'll need to do something different. And so I think there are greater challenges that are sort of the further you go out from the image domain. I feel optimistic. One reason I feel optimistic is that even when you look at something like a language model, we see word embeddings have these directions that are meaningful. And to the like in some ways the like most fundamental underlying sort of thing to our approach is like trying to understand what directions in these representations mean and study those. But I think there's a lot of work to be done. Maybe other people have comments.
Well, one of the things I'm really excited about is that there's multiple parts to the atlas, and if you step back from the feature viz part, right? So each cell is an optimization of an image, right? But you look at the parts before that where you say, okay, I have an embedding, right? Like I have a data point, I've run it through the model, and it's given me some representation of that data point, which is a high dimensional vector. You do that for all your data points or some subset of them, and you put that through the dimensionality reduction to get a map. Then you draw the grids over it. Can you come up with a way to summarize the data points on that map? Because if you can, then you already have, now you have a map of that data space organized by what the model learned. Even if you can't necessarily say this is what this word looks like, or these words look like to the model, you can say these words are similar according to the model. So I don't know, put a word cloud in each of those squares, or I've been doing some of this stuff with other kinds of sequential data. The quick draw stuff is interesting because even though it's still drawings, the data is not pixels or images. It's a series of points and strokes. So it's using a recurrent neural network to organize to learn the patterns. So in general, there's this way, like as long as you have some model that can give you meaningful representations of your data points, you can make a map of it. And that's an open challenge of like how to render that map, and something that I'm excited about and that we're working on right now, actually.
So I'll ask any closing thoughts or things you'd like to say.
So I think there's kind of like one class of response to this kind of work, and it's along the lines of how can this help me continue doing machine learning as I've been doing it. And I think that it can, and I think that we were kind of maybe struggling to have like these groundbreaking specific ideas in that way, but I do think that there are ways that this would help us have better ways of doing machine learning as it's conceived now. But the part that I'm particularly excited about is the space that this opens up in ways that we haven't been able to use it before. Like some of the ideas that we've kind of bandied about with this is like, what if this were like a palette for a painting program and you could dip a brush in any one of these ideas and then paint it? Or if you used it to search for images, you could use different activations from these different ideas and say, oh, I'm looking for images where it's like this on the bottom, but then there's like a fuzzy thing up here, and the proverbial like 1,000 words to describe an image kind of becomes a lot easier. It's like, how would you put that into words? Whereas here you can spatially arrange these activations and then use that as a map to like search through. It's a visual vocabulary. So you could create a word processor to both create or search for images. You can use it to like as a histogram of concepts to summarize millions or billions of images and say, oh, this image set here has lots of dogs in it, and this image set over here has lots of humans in it, and you can use this vocabulary. And so I think those sorts of ideas are the things that I personally get very excited about.
Let's thank our speakers. So please stick around. We'll have a brief pause, and then we'll do show and tell. So the thing I really like about this meetup is that we can show visualization projects we're working on. These can be GIFs or blocks or notebooks. Expectations are not high. A minute or two, something that's working, or maybe something that's not. If it's not and you have like a specific question, you're in a room full of experts and you might get an answer. So I'll quickly show an example, and I encourage you to do the same. You can bring your laptop, or we can open a new tab if what you want to show is on the web.
Well, and
thank you,
everybody,
Micah.
for coming out. I mean, this is I love talking about my work. I don't know about everybody else, but thank you for listening. So thank you. Yeah.